Okay, so the last time we introduced the idea of a symplectic 2 form, so now we can start talking about Hamilton's equations in terms of the symplectic form. Okay. Okay, so let's see what happens. So abstractly, you can write down Hamilton's equations in the following way. So it's oftentimes written as omega, which is, if you recall, the symplectic form, acting on the Hamiltonian vector field xh, which depends on q and p, paired with some arbitrary vector v, is equal to dh paired with v, okay, for all v, okay. If you know something about differential forms, it's like another way to rewrite this is that the contraction by the Hamiltonian vector field of the symplectic form is equal to dH. Okay, and so this is at the level of one forms now. It's like if you have a two form and you contract it by a vector field, then you just get a one form. Okay, so and again, it's like if you have one form, you always think about it as being defined in terms of its action on a vector. So what you do is that you test this by applying it to this, again, arbitrary vector v, right? And then you have dh equals to v. And then by definition of this contraction, all you're really doing in the contraction is that you have a two form, right? And you contract by a vector field, and that means that you substitute into the first slot this vector field, and then the second slot is whatever you were given, which is this v. Okay, so so this notation, if you will, is obviously equivalent to this, but sometimes people prefer this expression because then you don't have to deal with this sort of arbitrary vector v here. But again, if you're familiar with this idea of differential forms in exterior calculus, then these things are all equivalent. Okay, so I'm not going to belabor this part here. It's like if you've seen it, that's great. If you haven't, it's not critical to the class. So let's just work with this sort of simpler representation at the top and see what happens. Okay, so you have this, and then the way to sort of, if you recall, it's like we expressed the symplectic form. It's like acting on two vectors in terms of a bilinear form. So in coordinates, right? What we have is that this omega of xh comma v looks like the following. And then I'm going to write v in terms of components, and xh is just the vector field, right? So that's expressed in terms of q dots and p dots. So that's what I'm going to do here, q dot 1 to q dot n, and then p dot 1 to p dot n. Okay, so that's the xh vector written in component form. And then you have the symplectic matrix, 0, identity, minus identity, 0. Right, and these are all n by n matrices. So each of these these terms are n by n matrices. And then you have this vector v1 to v2n, which is arbitrary. Okay, so let's try to simplify this. Okay, so I'm going to multiply this row vector by this symplectic matrix J. Okay, so it's denoted J usually. Okay, and this looks like minus p dot 1 to minus p dot n, and then q dot 1 to q dot n, again paired with v1 to v2n. Okay. All right, and then you want to equate this as like to dh paired with v. Okay, so let's write down what dh is. So dh is the q1 all the way up to dh the qn, and then dh the P1 to dH dPn, okay, paired with V1 to V2n. Okay, so here this equality just comes from, well, I should say that this is dH paired with V, right? Okay, and then these two things are equal, so I'm just going to equate them. So it's easy to convince yourself that if you allow V to be arbitrary, what has to happen, of course, is that each of these row vectors have to be equal to each other component-wise, and then that gives you Q dot I is equal to dH dPi, and then P dot I is equal to minus dH dQi, right? So that's of course just the usual sort of Hamilton's canonical equations. Okay, and then you can ask, well, what happens more generally, right? So more generally, you can write things in coordinates. So we had talked about how, you know, it's like there was this J matrix which expressed the symplectic form as the mass matrix in a bilinear form, okay? And you could do this even for non-canonical symplectic structures. So you get some other J matrix, which is skew, but you know, it's like it would correspond to some other symplectic structure. And you can then ask, well, what is the generalization of Hamilton's canonical coordinates, Hamilton's canonical equations with respect to a non-canonical symplectic structure where you know some skew J matrix which it corresponds to. So, so let me say what it looks like in coordinates. Okay. So more generally, right? Right, we have in coordinates that the Hamiltonian vector field xh is equal to this J symplectic matrix, which may or may not correspond to a canonical symplectic structure times the gradient of the Hamiltonian. Okay, so this is something which, if you have done any physics, it's like in particular Hamiltonian mechanics, you might have seen before. Okay, so let me just stop here, and then the next thing we'll discuss is how you can, you know, think about the idea that Hamiltonian systems preserve the symplectic structure. Okay, so I'll stop for now.